Now let's talk about how oxidation applies to aldehydes and ketones. There are some simple definitions that work well for us in organic chemistry, namely that oxidation is going to be losing two hydrogens or sometimes gaining an oxygen. In a grand scheme of things, you could start with methanol as shown at the top, methane shown at the top here, and every time you add an oxygen or a bond to oxygen, it becomes oxidized. So we don't do an exact oxidation of methane to methanol, which is the next one here. But if you add another bond to oxygen, it becomes double bond O, and it had to lose two hydrogens to get there. And adding another bond to oxygen after the aldehyde that's shown here, then we would turn it into a carboxylic acid. So this is the general idea. When we increase bonds to oxygen, then we are oxidizing the hydrocarbon in this case. So if you take a carboxylic acid and oxidize it any further, that makes carbon dioxide. Now, the opposite of that is going to be reduction. I'll talk about that in a separate recording, but not immediately connected to this exact one. So increasing the bonds to oxygen is always going to be oxidation. Now, aldehydes in the presence of an oxidizing agent, as shown on the previous slide, are going to turn into carboxylic acids. Ketones do not oxidize. You can't add more bonds to oxygen without breaking bonds to carbon, and so these do not react. So if you take an example such as the one at the bottom of the screen here, where you have benzaldehyde, the one that smells nice, smells like almond extract, and it can give it an oxidizing agent, all you have to do is realize that the aldehyde group will be converted to the carboxylic acid group and fill it in accordingly. Not too tricky. Now, it has a name. The name of that hasn't been encountered previously, but here it is in case you'd like to see it. It's called benzoic acid. And so all we've done is turn the aldehyde group into the carboxylic acid group without being anything else to do. Nothing else changed. The interesting aspect of oxidations of aldehydes and ketones, well, is that it's only aldehydes, and there's a way to distinguish aldehydes from ketones because these qualitative tests have some nice visual effects. The first one is called Tollin's reagent. It's commonly used in labs we call it the silver mirror test because you're going to start off with a colorless reagent that contains a silver ion, and that silver ion is going to be reduced from silver plus to silver metal. That's what silver at the end here is, silver metal. It has no charge, so putting a 0 there represents that idea, but we don't often include that. The aldehyde, at the same time, is going to get oxidized because it's a mild oxidizing agent. And when it oxidizes, it's going to turn into a carboxylic acid, but it's going to be represented in the form of its ion, the conjugate base of it, but it's still a carboxylic acid in an ionized form. So the carboxylic acid results from the oxidation of the aldehyde, while at the same time the silver ion becomes reduced to silver metals. And so reducing the positive charge is a nice way of thinking about reduction in this context. The nice shiny silver surface on the glassware tells you that you have an aldehyde present, and it's literally the method used industrially to make silver mirrors. If you had a ketone in your solution, you will get no mirror whatsoever because it doesn't oxidize. So there's one example of a nice qualitative test using the oxidation characteristic of an aldehyde. The second one is sometimes called Benedict's reagent, sometimes a slightly different name, but close enough for this purpose. And they're going to be ones that include a copper ion. Copper ions are characteristically a nice blue color. It's a copper 2 complex. With what it's complex, we do not care here. And aldehydes and certain ketones that will get discussed in the context of carbohydrates will be oxidized. Aldehydes get oxidized. But at the same time, the copper 2 ion becomes reduced to copper 1. In other words, you're reducing the positive charge again. And when you do, the color is going to change because you begin with this nice copper 2. It's blue, nice visual cues there, and then it's reduced to copper 1. And that's an oxide, as it turns out. It's going to be a precipitate. It'll settle out from the solution. But again, this is a qualitative test. So the aldehyde will cause this reaction to give a nice color change. The ketone will not. It's often puzzling or easily mixed up, but oxidation and reduction have to occur at the same time. One substance gets oxidized, in this case the aldehydes get oxidized, while at the same time the metal ion gets reduced. So one is always accompanied by the other, even if we're not specifically looking for the second part. And these are examples of simple oxidizers that allow us to distinguish an aldehyde from a ketone. Here's another visualization for that. The copper 2 ion is reacting with the aldehyde. The aldehyde has RCHO as its abbreviation, and it's going to be oxidized to make a carboxylic acid, but it's shown in its ionized form, which is going to annoy you for now, but later you'll learn more about the fact that it really is just like having that hydrogen on there. It's just that it's a basic solution in the base, and these things are done in basic solutions to make them work. And so you can see some interesting color changes from the nice copper 2 to the copper 1 in the picture shown at the bottom. The green must be the half, somewhere in between the two. All right, now having talked about oxidation of these kinds of compounds in Tollens reagent, all we're looking for is what kinds of products are expected. Let's try some examples. So we have a funky compound here. It doesn't matter what it is, it's just a compound and we don't care. We'll just seriously take the aldehyde and turn it into a carboxylic acid. The rest of the molecule remains unchanged. So just put Tollens in here, Tollens reagent, and then we'll have to draw it. So 1, 2, 3, 4, 5, 6. If you can count, you get it, you'll get there. And then we'll put in corresponding hydrogens to make carbons look as though they've got 4 bonds until we get to the last one here. And now instead of an aldehyde, which we could name in a second, I'll go back to that, then we're going to turn it into a carboxylic acid. That one I'm not ready to name yet. We'll save that for a later chapter. So if you have 1, 2, 3, 4, 5, 6 carbons, it's hexanal. Pardon the extra line here. Maybe I can take that out quickly. Let's see. Oops, not so nice. Sorry. And then hexanal must have in its components here a 5-methyl group. Okay, and pretend that's all one word. All right, here's another one. Let's draw it, given the name. So 2,2-dimethyl pentanal, 1, 2, 3, 4, 5 is what pentanal tells us. So it's an aldehyde. You could draw the aldehyde on either end. It doesn't matter, but we kind of have a habit of putting them on the right. It doesn't make it more correct or less. All these compounds can be drawn lots of different directions and still represent the same thing. So put 2 methyl groups on carbon 2, knowing that the aldehyde is always going to be carbon 1. With Tollens reagent, we're going to oxidize the aldehyde and turn it into a carboxylic acid. No further thinking, no further complication. So take that carbonyl, leave it as is, turn the hydrogen into an OH. This is where we add oxygen when we oxidize. And the rest of the molecule stays unchanged. We won't name this one at the present. When you learn about carboxylic acids, you'll recognize that the name is going to be very, very similar to what the name was as the aldehyde. Okay, so treating compounds then with Tollens reagent. Let's do one more. 2-methyl-3-pentanone. Let's draw it. 1, 2, 3, 4, 5. And there's your carbonyl. And put a 2-methyl over here and subject it to some oxidation. Think hard. What are you going to do? So Tollens reagent, and each of these cases the silver ion would read, or silver metal would also be in evidence to verify that it was a positive test. In this case, no reaction. This is a ketone. Ketones do not oxidize. Nothing more to say. Okay, let's do another example or two. A further question, however. Would the products be different if Benedict's reagent were used? No. You just have a copper 1 as that's red as a product. Otherwise, the organic part is the same. And different visual cue is all that is. All right, couple more. What would you get if you would do something else? Let's do reduction. Let's think for a moment here. Actually, I wanted to do another oxidation. So let's do the vanilla compound and see what would happen if we oxidize that with Tollens or Benedict's reagent. So Tollens reagent, these should feel very similar by now. And you're going to oxidize the aldehyde. And so draw your benzene ring, put in a circle to represent that it's aromatic, leave most of the compound unchanged. The alcohol is also not being affected here. This is a reagent specifically used for aldehydes and ketones, and so turn it into a carboxylic acid. That's all you have to do. With Benedict's reagent, nothing different happens, except you're going to get the copper 1 ion in the solution, and this one is going to give you this silver ion or silver metal as a precipitate, and this has a color. Well, this has a shiny silver appearance on the glass for that kind. All right, so I think this is all the examples of oxidation I wanted to give. I will make a recording that discusses reduction separately. I hope you find this helpful. Good luck on your studying. Please ask lots of questions. See you in class.